Thank you for listening to my talk on regularization with stochastic transformations and perturbations for deep semi-supervised learning. We propose an unsupervised loss function which can take on two forms. In the first form, we minimize the difference in prediction caused by data augmentation. So if I have a sample for which I do not know the label of, I can create many transformed versions of it, such as geometric transformations, and pass them all through the same network. And at the end, I expect that all of these transformed samples would result in the same prediction. Therefore, our loss function takes on the form of sum of squared differences between the predictions of pairs of samples passed through this network. Notice that this is an unsupervised loss function because I do not need to know the label of the original sample to construct it. And it can be combined with a traditional supervised loss function to create a semi-supervised learning algorithm. In the second form, we minimize the difference in prediction caused by stochastic perturbations of the network itself, such as dropout and randomized pooling instead of data augmentation. So again, if I have a sample for which I do not know the label of, I can pass the same sample through many randomly perturbed versions of my network, and at the end, I expect that the prediction vector for all of these passes should still be the same. So the unsupervised loss function still has the form of sum of square differences of the prediction vector between multiple passes. So that's the idea of the paper. Now moving on to some. First, we worked with the MNIST dataset, and in this case, we did not use data augmentation, but minimize the difference in predictions caused by dropout and randomized pooling. And we compared this to the previous state-of-the-art ladder networks when using only 100 labeled samples that are available. Ladder networks was able to obtain an average error rate of 0.89% in this case. We are able to obtain, with 100 samples, labeled samples, a 0.55% average error rate. And notice that this is not too far off from the error rate when using all of the labeled samples available for this dataset. Next, we study the behavior of the loss function as a function of the amount of labeled data available. And notice that the error rate climbs a lot slower when decreasing the amount of labeled data available if one uses the proposed unsupervised loss function in addition to the supervised loss function. And finally, I want to note that for CFAR 10 and CFAR 100, even when all of the labeled samples are used, the addition of the proposed unsupervised penalty results in improvement of accuracy and state-of-the-art results. Thank you for your attention.